When most people look at an X-ray tube, they see a piece of medical equipment. But when I look at it as an engineer, I see something totally different. I see a machine that's locked in this constant, ferocious battle against itself. This is really a story about surviving incredible heat.
And that brings us to the one big question, right? This is the fundamental challenge that has pushed every single innovation in X ray tube design for, the last century. Because to get those powerful X rays we need for modern medicine, you have to generate an absolutely insane amount of heat. Just look at this number for a second 99%. That's how much of the electrical energy we pump into an X ray tube is instantly wasted as heat. Just 1% actually becomes the X rays we want. So, you see, our real job as engineers isn't just making X-rays. It's figuring out what on earth to do with all that destructive heat.
Okay, so to really get how we win this fight, we've got to map out the battlefield first. Let's take a look inside the machine at the key players.
The basic idea is actually pretty straightforward. Over on the left, you've got the cathode, the negative side. Think of it like an electron gun. On the right, that's the anode, our positive target. We just fire a super high-speed stream of electrons from the cathode, they slam into the anode, and bam! That collision creates X-rays. And all of this has to happen inside a vacuum so the electrons get a clear shot.
So let's break this down. The vacuum envelope, that's our clean room, no air allowed. The cathode is basically a tiny, superheated tungsten filament that literally boils off electrons. And then there's the anode. That's our target. We make it out of tungsten because it has a crazy high melting point. And trust me, it needs it, because this is ground zero. This is where 99% of that energy turns into pure, concentrated heat.
For years, that intense heat was the ultimate bottleneck. It would literally melt the anode, just destroy the tube. But then came the game changer, the absolute hero of our story, the rotating anode. This wasn't just a small step up. It was a total revolution in how we manage heat.
And you can see the difference clear as day right here. On the left, that's the old way of doing things, a stationary anode. It's just a block of metal that sits there and takes a beating, soaking up all that heat in one tiny little spot. But on the right, that's the rotating anode. It's not a static target anymore. It's a dynamic disk, a whole new way of thinking about the problem.
The numbers here really tell the whole story. With a stationary anode, all that energy is blasted onto a focal spot that's sometimes just 1/10 of a millimeter wide. But by spinning the target, we spread that exact same amount of energy over a circular track that can be 600 millimeters long. The effective area is huge, increasing the heat capacity by up to 100 times. No more destructive hotspots.
Here's a really simple way to picture it. Imagine you're trying to cook, but you're just holding a blowtorch to one spot on the frying pan. You just burn a hole right through it, right? Well, the rotating anode is basically the engineering version of constantly stirring the food or moving the pan around, making sure no single spot ever gets hot enough to cause damage. It's brilliant.
And it does this at mind-blowing speeds. To keep up with something like a modern CT scanner, these anodes can spin up to 10,000 revolutions per minute. That's spinning faster than the engine in many high-performance cars. It's just an incredible piece of engineering, and it's all happening inside a perfectly sealed vacuum. But here's the thing. The rotating anode, as amazing as it is, doesn't work alone. It's definitely the star of the show, but it has a whole supporting cast of other cooling systems, all working together to get that heat out of the tube and away from everybody.
This diagram shows us the next critical line of defense. The entire vacuum tube assembly is literally submerged in a special kind of oil. And this oil isn't just for lubrication or anything like that. Its main job is to pull heat away from the glass through a process called convection. So the heat actually goes on a 4-step journey to escape. First, conduction pulls the heat from that tiny focal track into the main body of the anode disk. Second, the glowing hot anode radiates that heat across the vacuum. Third, convection carries the heat from the tube through the oil to the outer housing. And finally, that housing gets rid of the heat, dissipating it into the room, usually with some help from cooling fans. It's like a beautifully choreographed relay race for thermal energy. And that really brings us right back to the main idea, doesn't it? This quote just nails it. Making the X-rays, that's the easy part. The real genius, the true art of the engineering here, is in managing the absolute beast that is the heat it creates. So why do we go through all this trouble? I mean, what's the actual payoff for this ridiculously complex battle against heat? Well, it turns out that pretty much every major leap forward in medical imaging depends completely on it. Better cooling is the secret weapon behind the tools your doctors use every single day. It's what makes a high-power CT scanner possible, letting it take hundreds of images in just a few seconds. It's what allows a surgeon to use real-time imaging during a long and tricky procedure. At the end of the day, solving the heat problem means doctors get faster, clearer images, and that means better, safer care for all of us. Which leaves us with a pretty fascinating question to think about. Our demand for more powerful, faster, more precise imaging is only going up, so this engineering battle is far from over. The problem is still the same, so what's next? Liquid metal bearings? Some kind of new nanomaterials? The next huge breakthrough in medicine might just be hiding in a clever new way to keep things cool.